Thanks, Luca. So today, in this talk, I will discuss about three European projects. One is ended a couple of years ago. Two are still running. So what I'm going to show you is not my research. It's the research of tens of people. So, because, as you probably know, European project involve research from different countries. So what I will talk to you today is how to use AI, so artificial intelligence, in robots for surgery. Okay. About me, I can skip this part, at least the left side, just to mention that I'm with the Department of Engineering for Innovation Medicine. That is a new department at the University of Verona. There are two sections. There one that is called Engineering and Physics, and another one, Innovation Medicine. So there are 25 engineers and physicians, and 39 actually surgeons or doctors. And we have also a few bachelor degrees on computer engineering for robotic and intelligent systems, human-centered medical system engineering, and then we have a master degree on computer engineering for intelligent system, and another master degree in medicine that will start next year. And we have also a PhD program. Okay, so about AI, I will start first with, with this book. So if you don't know what to read during the summer, this is a great suggestion. So Thinking Fast and Slow by Daniel Kahneman. He was awarded with the Nobel Prize in Economics, even if it is a psychologist, actually. So in this book, he mentioned that in our brain, we have actually two systems. The system one, that is actually the one that is thinking fast, and the second one that is the one that is thinking slow. So the system one is, help us during choices or tasks that doesn't require much effort. So it's the sort of action and task that we do by heart. So they are impulsive and intuitive. And what is important, and the reason for which I talk about that will be clear later, this thinking fast, the main approach is to view if there are in the previous experience something that is close to the task that I need to solve, and then apply the same solution. Thinking slow is, on the other hand, when we have to tackle tasks that are quite complicated. So we have actually to stop and start reasoning. You don't have to go very fast, but we have to actually spend time. And for this reason, as everyone experienced, this way of thinking is usually more difficult and often also lazy. So if you want to translate these two systems in a sort of cyber-physical system, well, the first part, the thinking fast, could be the one, the role played by artificial intelligence, while the thinking slow, the one that should be done by, in this particular case, by surgeons. Then, this is a meme that was quite famous a few years ago. Usually, when you talk with computer scientists, then they promise you a lot of things, but at the end of the story, unfortunately, the results are not often what you expected at the very beginning. And this is something that we experience also in the project that I will show you. Then, before starting the discussion of the project, I would like also to share sort of two cartoons about AI and accuracy, and the next one. Suppose that you are a software engineer or a control engineer or bioengineer, so that talk with a surgeon. So would you like to use an autonomous robotic system controlled by AI algorithm? of course, AI is super cool. We have an algorithm that has an accuracy of 95%. It sounds great, but wait a minute, 95% means that one decision out of 20 is wrong. And these kind of systems are supposed to make decisions many times per second. So I prefer to stay in charge. And of course, from our side, surgeons are difficult client. Another thing is about AI and training. So the same question, would you like to use an autonomous robotic system controlled by AI? Yes, of course. Could you help us in labeling the images to generate the data set to train the neural network? No problem at all. Then wait a minute. On a 4-hour-long procedure, even if I label just one image per second, there are more than 14,000 images. And then we need hundreds of procedures to train neural network. And of course, that is the reply of surgeon and what we as an engineer think. So these are two provocative slides, but that have some truth. And we should take into account this thing when you design a robotic system with an embedded AI algorithm. So the first project that I would like to talk to you is called, the acronym is SARAS. SARAS stands for Smart Autonomous Robotic Assistant Surgeon. And this is what you see in the operating room during robotic minimally invasive surgery. So there is the main surgeon that is here seated at the Da Vinci console. And then there is another one, the assistant surgeon next to the patient. In the future, this is what we would like to have. So I took this piece of video from the Prometheus movie. So it is a 10 years movie. And you see that there is the main character of the movie that enter in this cell, just put in her mouth these plastic things, push 2-3 buttons, and then everything goes by itself. Of course, there is an alien in her belly, but that is standard stuff. And the interesting thing is that in the vision of the surgery in the future, there are no surgeons. So, and the goal of this project is was actually to develop the next generation of surgical robotic system that will allow a single surgeon to execute a robotic-assisted minimal invasive surgery without the need on an expert assistant surgeon. So we want to substitute this guy here with a robotic system. Oh, sorry. Okay. And before entering into some details, I would like also to talk about the difference between automation and autonomy. So nowadays, autonomy is everywhere, but I mean, the boundaries between automation and autonomy is really fuzzy. So you can think about automation as the ability to perform repetitive actions without human intervention. So the main characteristic is that the environment is actually well structured, and the procedure that you have to do is well known. On the other hand, when you talk about autonomy, that is the ability to perform complex action without human intervention and to make decisions that require reasoning, the environment is not well known, and so you cannot pre-program everything. So this is a very important distinction. Of course, these are the definition that I'm used to, but of course there are other definitions that you can use. So this plot, this picture actually is coming from a very famous paper, and describe the different level of autonomy in a surgical context, from zero, actually where we are nowadays with the Da Vinci robotic system that is the state-of-the-art since 2000 something, and with all different level of autonomy. So no autonomy, robot system, this is level 1, task autonomy, conditional autonomy, high autonomy, and full automation. So as I said, we are here, with or without the robot, and what I showed you before is a level 5. And what we would like to tackle are the kind of autonomy in level 2 and 3. So task autonomy and conditional autonomy. So I would like to show you a video that describes everything. Oops. Okay.
During the project period, the SARA's teleoperated system was used in various testing sessions to collect data necessary to train the artificial intelligence modules of its autonomous system release, called Solo Surgery Platform. It consists in a pair of cooperating and autonomous robotic arms, holding laparoscopic surgical instruments, entirely taking over the role of the assistant surgeon during a minimally invasive procedure. To this extent, research efforts have recently been concentrated on the development of the SARA's cognitive control architecture, consisting of a perception module that takes care of understanding the complexity of the surgical area, detecting the position of organs and laparoscopic instruments, an advanced user interface for the first surgeon seated at the Da Vinci console, comprising the positioning indicators of the SARA's instruments out of the surgical field, and the main surgeon's vocal commands directed to SARA's arms. A cognitive control architecture that decides the next surgical action to be performed by the SARA's arms to help the first surgeon. A planning and navigation module, translating the autonomous decisions made by the cognitive module into appropriate collision-free trajectories for the SARA's tools. During spring 2021, expert urological surgeons tested the Solo Surgery Platform by simulating phases of the robotic-assisted radical prostatectomy on advanced human abdominal phantoms developed during the project. The tasks executed by the SARA's platform were successfully accomplished. Moreover, recovery actions were properly implemented to take care of unexpected events and errors that may occur during the procedure. The research work that led to the integration and validation of the...
Okay, can stop here. So the objective of this project were actually three. The first one is the translation of the medical knowledge into an engineering formalism. This seems easy, but it is not, because you cannot go to a surgeon and ask him, so please tell me how many newtons do you apply when you push down an organ, or you do some, or how many Newton meter you apply when you insert a needle. So these kind of things that are quite important for us are actually, should be collected in a different way. Then we designed this perception module that were able to understand the status of the procedure in order to help the main surgeon in the proper way. And then this cognitive control model that actually makes the decision to and then to put in action the task. Okay, this is the impact that you wrote in the proposal, because I know in any European project we have to write a section about the impact. So in our case, to decrease the cost per procedure, to increase the surgeon awareness during the procedure, and then develop a sort of network of researchers on autonomous or semi-autonomous, as in our case, devices. And about the knowledge, this is a quite important point. So there are actually two ways to do these things. The first one is what is called end-to-end approach. So it's a sort of a black box approach. So you put there all the measurement that we have from your system, all the videos that you collect from the endoscope, all the knowledge that you can write in some way, shake it, and then you expect that gold is coming out. That it doesn't work, because there are a lot of knowledge that it is very difficult that a single neural network is able to understand. Then, so we moved on the engineering stack. So we used AI tools for semantic segmentation of the scene, to understand the status of the procedure, these kind of things. But everything was embedded in, I would say, standard in a standard control architecture. So we had a supervisory controller, then the high-level controllers, and then at the end, the standard lower the inner controller that are the one closer to the robotic arms. So this is the approach that we adopted in our project. So at the end, just to sum up, so we need to integrate the medical knowledge, the action recognition and prediction, the supervisory controller. Then we have the multi-robot cooperation. We have 2 arms. Then all the trajectory planner, that of course must be a system that plans collision-free trajectory in an environment that is dynamic. And then the low-level controllers. And at the end, I mean, at the very core, there is always the surgeons. So this is the block diagram that we sketched at the very beginning. So there are different colors, and now I will go through pretty quickly on the different pieces that make up our puzzle, technological puzzle. So we started with the medical knowledge and the preoperative data. So we have annotated data set from real procedures, as this one, but also on procedures on mannequins, the phantoms that you heard about in the videos. Then there is all the registration. So we have preoperative images, so MRI, computer tomography, or whatever. And then we have to register this preoperative information on what we see during the procedure using the endoscope. And this is not at all a trivial thing to do, but it's fundamental, because otherwise you don't know where to move the tools, the instruments that our robotic arms move to help the surgeons. And then the most important part probably is the representation of the surgical procedure. Use state chart formalist, that is a sort of parallel final state machines that are quite easy for humans to understand, and also you can write them in a way that also a machine can interpret. And we focus mainly on the prostatectomy procedure, so the procedure where the surgeon had to remove the prostate. That is a quite sequential procedure where not many strange things could happen during the procedure. And these are the properties that actually for the reason for which you choose these formalism among many others that have been developed in computer science. So it is robust, modular, flexible, and we can integrate together bottom-up and top-down knowledge. So the surgical knowledge, the top-down, and the data during the intraoperative procedure in the bottom up. Then the second part was the human-robot interface and the interaction. So we had haptic devices. So the main surgeons can feel the interaction with the environment. And for this reason, we mounted on, we put on the laparoscopic instrument these strain gauges that measure the deformation of the tools when they are in contact with the environment, so we can estimate the force at the tip of the tools. And then there are several virtual features, so you can show on the display other information, such as what the robot is doing, what is going to do next, in which phase the system thinks the procedure is, and a lot of other information. And there is the speech recognition, so the system can understand a certain sequence of commands that we define at the very beginning. Then we have all the AI related to the perception, so the semantic segmentation. So to understand what we are seeing in the endoscope images, so the different organs, the different tools, and then reconstruct actually the 3D model of the system. And then, as I said before, everything must be registered. So when you see something in the images, we have to be sure that how it is related, a certain organ, with the position of the laparoscopic instrument that we are controlling. So everything must be registered. And since we are in a dynamic environment where a piece of organ appear and disappear, this is not a trivial task at all. And then we have another part of the AI system, so what we call the cognitive architecture. So it consists of the main part is the phase segmentation. So using the video streaming and using the kinematic of the robot controlled by the surgeon and our robot, and using a proper network training on all these heterogeneous data, we were able to decide in which phase the procedure is with a certain probability, and then that is useful for the decision maker to decide what to do next. Then we have the standard planning and navigation. The environment is quite complex, so also these things, also these algorithms were not trivial, and in particular because when you move the instrument, they cannot move freely. So in laparoscopic surgery, you know, they inflate the belly, then they put a trocar on the belly, and only through this trocar that are actually the hole, they can insert the instrument. This means that they cannot move everywhere, so they are constrained. Instead of 6 degrees of freedom, you have only 4. And so when you design, when you plan your trajectory, you have to take into account also these constraints. And then at the very low level, we have the controller, and in particular, we implemented a model predictive controller because we needed to integrate some constraints. So we want to stay away from organs that we don't want to touch. We don't have to collide with the other tools. So using this kind of approach was quite interesting and actually worked pretty well. So the take-home messages about this project is that when you integrate different technologies in a complex system, we have to pay attention on how we embed the different things, because I mean, the strength of a chain depends on the weakest link. And when you put different tools that everyone is not working perfectly, then of course what you have at the very end is something that works very bad. So, and then another interesting things is how you represent the knowledge. Here I'm talking about surgical robotics, but the same things can be the same problem arise also in cooperation, robot cooperation in industry or in other things. So when we have to cooperate with a robot to perform a task, in that case, the knowledge of the task is fundamental to be properly written, both for the human and for the digital system. And then there is all this buzzword about trustiness and explainability of AI that I don't want to talk about. So another project is called a robotics. This is ongoing, and we are the second year right now. So is AI robotics for the diagnosis of prostate cancer. And I will show you some numbers that are quite, first of all, this project was an EIC project that is another pillar of funds from the European Commission. And we have in the past several other European projects. And at the end, we managed to found a company, a startup, and then we got this project funded by the European Commission in 2023, so last year. So this is actually a long story that brings to this project that has a higher TRL. So at the end of this project, we should reach a TRL 6 that corresponds to the preclinical trials. So actually, in this project, you are supposed to do not research, but only innovation. Okay, why is it scary, the prostate cancer? Okay, there are a lot of new cases every year, but the scary thing is that 1 man out of 9 will have the prostate cancer. So more than the 10%. So this is scary numbers. And when before actually go on with the radical prostatectomy, so the removal of the prostate gland, there are the biopsy. That is actually the only things that the surgeon can rely on to confirm if a cancer is there or not. Because then with the biopsy, you extract some tissue, then the tissue is analyzed, and then you have the final result. Unfortunately, there are 25% of false negative. And in a moment, I will explain why. And so there is the possibility to have under-treatment or over-treatment. That are something that we want to reduce. So the vision of this project and also of the company is actually to improve the quality of the biopsy in order to have a better treatment for the patient. So these are the unmet needs of urologists. So we need to identify the lesion in a more accurate way. You have to perform the biopsy in a very fast way, and in particular for therapy, it is necessary to go back in the same position where you detected a lesion. Nowadays, this is not possible because they actually play, I don't know in English, but in Italy is battaglia navale, so naval war. So they have this grid and then start to inserting needle like hell. So 20, 25 needles in order to cover all the prostate, instead of going precisely where the lesion should be. So, and the reason for which there are these false negatives are mainly four. So the targeted identification is an issue. Then there is a problem with the image fusion that I will talk about in a moment. Then to insert the needle in an accurate way, and then to have a sort of workflow that help the urologist to perform in a better way the procedure. Pay attention that the biopsy, despite it's important, is always done by a resident. So surgeons that start their career, as soon as they are good enough, they are moving somewhere else. So actually, the biopsy procedure is always in the transient phase. That is quite scary too. So how we want to tackle and hopefully solve these challenges. So the first one is the target identification. We are developing an AI procedure that automatically contour the prostate and the lesion in MRI images, so in preoperative images, and construct and define the 3D model of the prostate also using the US images, so the ultrasound images that are the images that you see when you actually perform the biopsy. Why you need these two models? Because MRI is a very accurate, so you can see also the lesion in these images. In the US, in the ultrasound images, you cannot. So that's the reason for which is very important this second step, so the image function. So you have to deform the MRI image, the MRI 3D model in the shape of the 3D US model, and also move the lesion in the proper, in the expected position. When you do that, then you can insert the needle using a robotic system in order to go there in a very precise way. Of course, you have to register everything. So there is the the preoperative images, the ultrasound images, the robot holding the US probe, and the robot itself that will put the needle in the right path. And then there is the workflow, so in order to standardize the procedure. So these are actually the overall system. So we started with, as I said, with the MRI segmentation of the prostate. Then there is the detection of the lesion in the MRI. Then we have intraoperatively the 3D model of the prostate using US images. And then you put everything together, so you fuse the intra and the preoperative images in order to have a good model of the prostate, and in particular to know very well the position of the lesions in the reference frame of the robot. Okay, here are some details about the prostate segmentation. So the people working on this stuff use the ResNet, so pre-trained network, and we have also a fine training on the images that we collected from different hospitals in the Veneto region and in the Emilia-Romagna. Okay, and then there is the segmentation on the US images. So this is done in real time. And this is quite important because every time you perform a biopsy, they use a sort of gun. So, and the people here is not in total anesthesia. So they are in local anesthesia. And when you shot a needle, then you cannot stay still. So actually, when you move slightly, then the position of the lesions are no more where they were before. Our target is to go to take samples of lesions smaller than alpha centimeter. So you can imagine that all the inaccuracy in the 3D segmentation, the fusion, in the robotic system. So at the end of the story will be a very challenging thing. And since after every biopsy, you have to actually register everything. So the segmentation of the prostate in the using US images must be very fast. So it takes less than 30 seconds. And then there is the fusion. So there is the rigid fusion where they actually try to match more or less the two reference frame using rigid rototranslation. But what we want to do is to have a sort of morphic deformation of the 3D model in order to also take into account the stiffness property of the prostate in order to have an accurate position, a more accurate position of the lesion in our model. Okay, these are some. Okay, I skip this video because it is just what I described to you. So since we are a bit later. And this is the prototype that we presented at the European Robotic Forum in March this year in Rimini. So there is a trolley, a passive arm, then we have a handle here that actually helps the surgeon to insert the ultrasound probe in the poor patient, in this case this mannequin. And then on top here, there are the robotic arm that actually guide the needle where we want. Okay, so that was the second project. The third one is called guidance. It stands for AI guidance for robot-assisted eye surgery. So now we move in a completely different anatomical area, so eye surgery. And as you can imagine, everything is scaled down by one order of magnitude because an ocular, I mean, our eye have a diameter of a couple of centimeters, while in the belly we talk about tens of centimeters. So here the accuracy is quite important things. So this consortium I mean, this project is not a research and innovation action, it's an innovation action. So this means that also in this project, we are not supposed to do research, but just innovation. And we have an important player here. We have Zeiss, that actually at the very beginning was not part of the consortium, but during the time, I mean, when we submitted the proposal and when we got founded, Zeiss acquired Precise, so the company that had the robot. So then Zeiss entered in this project, and of course, now everything must be kept secret. So the problem with the I mean, the disclosure of things is even more important. So the eye surgery is critical in several aspects. So you need micro surgical instruments, so less than 1 millimeter. Yeah. So they have graspers that are almost invisible. The tissue is very delicate, and I would say an error in positioning of tools during the eye surgery could have a very bad impact on the quality of life of patient. And another interesting, I mean, another challenge is the depth perception. So during the surgery, they have this sort of laser. So they put the light within the eye. Then you have a microscope through the eye, and then they have this very tiny instrument. So the first problem is that there is no 3D vision. And the second thing is that it is, in order to know how close, for example, the tools is to the retina, the only information that they can use is looking at the shadow that the tools does on the retina. So, I mean, it is very, I mean, quite a difficult kind of surgery. So our idea is to improve the robotic system that they have, and using some AI algorithm to perform, to help the surgeon in some phases of the procedure. The first one, to understand how close the tools is to the retina, to propose eventually best trajectory to execute, for example, the peeling procedure. Peeling means that on the retina, you have a very thin layer of tissue that you have to remove. And so you have to remove this layer, but of course you don't have to damage the retina. So grasping this piece of tissue is quite challenging. And another thing that we want to embed in this system is a bilateral operation architecture. Bilateral means that the operator perceives a force feedback when he or she is touching the retina, or, as in our case, we create a virtual obstacle. So, for example, the retina, if in a certain procedure, phase of the procedure, you don't have to touch the retina, then you create a sort of no-fly zone. And when the tool is closer to the retina, you perceive a force that pushes you away. But of course, when you have to touch the retina for the peeling procedure, this modality should be switched off, and we have to provide other feature to help the surgeon to grasp this tissue in a very precise way. Here we were in the operating room, and where I have my first experience of ex vivo human eyes. That is something that I will remember forever. But I mean, everyone is, I mean, happy, but I mean, it was quite traumatic at the very beginning. So this is the block diagram of the system. So we have an active device with the force feedback. Then there is the robotic tools. And then what we are going to develop is on one side, visual and acoustic feedback. And on the other side, the haptic feedback. So the surgeon can perceive how close it is on the anatomical structure with the force feedback, but also with acoustic feedback or some information that is superimposed to the microscope. And so these are, I think, the only equation that you will see in this presentation. So this is the bilateral teleoperation architecture that we implemented. So at the operator console, the force feedback is just proportional to the difference between where the operator would like to be and where the tools is actually because of these virtual boundaries. While at the remote side, so the patient side, we have this OCT A-scan that is a technique that we use to measure the distance between the tool and the retina. Then, thanks also to this measurement, you can define a 3D model of the retina, at least in the region where you want to work. And so you can know how far, what is the distance between the tool and the retina, and approximating the 3D model with a certain number of planes, you can provide to the operator the sort of virtual feedback in order to prevent him to damage the retina. So this is the optimization problem that we solve at a time. I'll describe it in a moment. So this is the overall architecture. And what is interesting is that at the operator side, we have a force torque controller, while at the remote side, we have a velocity controller. Why not position controller? Because some of the constraints that I showed before are easy to solve in velocity. So actually, we computed the desired velocity, then we integrated this velocity, so we have the desired position. So this is what I already talked to you about the operator side. So this is where the operator, where the surgeon, the Cartesian coordinate of the active device. This is the Cartesian coordinate of the remote robot. If the robot is following perfectly the command from the surgeon, this arrow is equal to, this difference is equal to 0, and so the operator doesn't perceive any force feedback. But when there is a discrepancy, then the operator perceives a force feedback, and we can generate this force feedback mapping the force and torques in the Cartesian space, in the joint space, using the transpose of the Jacobian, the geometric Jacobian matrix. The remote side is quite challenging, is the optimal problem that I showed before. It is more complicated because we have to take into account the kinematics constraint of your robot, both in the joint space and in Cartesian space. We have to consider the remote center of motion. In the robot that we are using, the center of motions is guaranteed mechanically. So actually, you cannot translate your tools through the hole that actually allow you to move the tools inside the eye, but you can only pivoting around it. But you can think of other robot where you have to force the remote center of motion via software. Then we have the workspace constraints. So all these virtual boundaries that we create to avoid the collision with anatomical structure that we don't want to damage. And then everything is considered using the passivity theory that help us to guarantee that the overall system is stable, even if we have, for example, communication delay or other uncertainty. So this is actually the problem that we have to solve attaining sample time in the remote side. So this is the output, so the optimal velocity. Then we have the performance index, that is a quadratic way of the velocity in the joint space. Then we have these xd dot and omega d are the desired linear and angular velocity that are coming from the haptic device at the operator side. And QD should be the desired velocity, but you cannot put underscore d here because in order to the other constraint and the other limits, it is well possible that this is not what we are supposed to have according to this Cartesian velocity. That is the reason for which there are these variable here, slack variable. Then we have this inequality for the remote center of motion. Here there are no slack variables because this must be a hard constraint. Otherwise, you can damage the eye. Then there are velocity limits, both in the Cartesian and in the joint space. And this set of inequalities that describe in a linear way the no-fly zone, so where the tools cannot go. And then we have the last inequality that actually is the passivity constraint that guarantees that the overall architecture is passive and so stable. And as I mentioned, there are these slack variables to allow approximation with respect to the position that where the surgeon would like to go. Okay, another thing, this is not an European project, but is still quite interesting as a sort of use in a real application of some research. So we developed and patented actually an endoscope, a visible thermal endoscope. Here the problem is still the prostatectomy. So suppose that a patient has to have his prostate gland removed. That is fine. Unfortunately, around the prostate there are a layer of tissue, and within this tissue there are very important nerves for men. So the one related to the continency and the sexual power. And as you know, when you cut or damage a nerve, then everything's gone. So you cannot do anything else to repair the nerves. What is the problem? The problem is that the nerves are thinner than hair, so they are almost invisible. They know where more or less where they are, so they try to stay away. But unfortunately, they use electro scalpel. So even if you cut in a certain position, the heat is moving everywhere else. And so it is possible that you can damage the nerves, not mechanically, but due to the temperature. And nowadays they have no idea how the heat is spreading over the anatomical structure. So what we developed is these things. So it is an endoscope with, okay, there are two standard cameras for the 3D vision, and in the middle, a thermal camera. Everything is registered. So what we can do is that during the procedure, you can superimpose to certain region the temperature. And if the temperature is getting higher than a certain limit that is around 60 degrees, then we send an alert to the urologist that should start cutting somewhere else in order to make the temperature goes down. So here there are different challenges that we have to tackle. So first of all, the multispectral images, so register visible and thermal images. Then also the temperature, the measurement of the temperature using thermal cameras is not at all a trivial things. And then we register the two cameras in order to have a sort of a 3D model in the thermal domain. So we know how the temperature, so the measurement, the temperature measurement is distributed in the anatomical structure that is under investigation. So I would like to conclude with a few take-home messages. So robotics and AI give surgeons super skills to perform the task they have to do daily. They need better sensing in order to perform this task in a more accurate and safe way. And the last things that is, I mean, one of the few slides that I showed at the very beginning, AI is demanding in terms of training, robustness, and so on. So all these things must be taken into account. So another thing that you should think of is, instead of moving from the, you should think to move from the artificial intelligence to the intelligence augmentation. So to provide to surgeons better tools, better sensing system to perform their task in a better way. So I have also included an advertisement. So we are organizing in July a PhD summer school in Verona for on control of surgical robot. Will be a hand-on schoolers, and the idea is written here. So DVRK is the Da Vinci Research Kit. So we have a Da Vinci robot in our lab, and the Da Vinci Research Kit is all the electronics that you need to buy to use the robot, because of course to use the robot and create your own algorithm, because of course you cannot use the software that is of the intuitive system. And will be in July. And that's all from my side. So thank you for your attention.